So I thought today I'd explain the minimum about string perturbation theory that every quantum physicist should know. So that means we won't get into details like the central charge and the critical dimension. There are all kinds of fun things that you should learn about if you actually want to do string theory. I'm only going to explain today things that you should know about even if you don't want to do string theory. So when we look at a Feynman diagram, we assign a propagator, which 1 over p squared plus m squared to each line. I'm going to write my propagators in Euclidean signature. And we can write the propagator in terms of a Schwinger parameter as the integral from 0 to infinity dt of the exponential of minus t times p squared plus m squared. So every line in this graph has a propagator. So this graph happens to have, I think, 9 lines. So there are 9 propagators. And each of those propagators, we assign to it a Schwinger parameter. I got tired of labeling them, so I only labeled 3 of them, but we're supposed to label all 9 lines in the propagator with a Schwinger parameter, which is a positive real number t. And then for each propagator, we write it as the integral over the corresponding t of each of the minus t times p squared plus m squared. Now, it's convenient to think of the Feynman graph gamma. What I've drawn here is the Feynman graph. It's convenient to think of it as a 1 manifold. So the lines in the Feynman diagram are nice, smooth 1 manifolds. The graph as a whole is not a smooth 1 manifold because there are vertices. Interactions happen at vertices where different lines meet. But the Feynman graph is a singular 1 manifold. And it had to be singular because there aren't enough 1 manifolds otherwise. A smooth 1 manifold is either the real line, or it could be a circle, which is OK at one loop, or you could have a piece of one of those, an interval. But the supply of smooth 1 manifolds is pretty limited, so Feynman had to use singular ones, which are Feynman graphs. Now, what it means to assign a length to each leg is just that the graph has a Riemannian metric. By what it means to place a Riemannian metric on the graph is what you think it means. On each 1 manifold making up the graph, we have an ordinary Riemannian metric, which is a length element. And in 1 dimension, a Riemannian metric is a 1 by 1 matrix that just tells us the length of a little piece of line. But up to diffeomorphism, there's only one invariant. The only invariant of a metric on an interval is its length. So when you look at the Feynman graph labeled by the Schwinger parameters, what you're seeing is a Riemannian graph, a 1 manifold, a singular 1 manifold, with a Riemannian metric, which is given up to diffeomorphisms. So as I just said, up to diffeomorphisms of the internal lines in the Feynman diagram, the only invariants of the metric are the lengths of the line segments, which are the Schwinger parameters ti. Now, although each line in the graph has its own momentum p, we don't just integrate over the p's independently. We have to impose momentum conservation. And we impose momentum conservation at each vertex. So here's a vertex with incoming lines, let's say, of momentum p1, p2, and p3. So we need a delta function, 2 pi to the 4th times delta 4 of the sum of the incoming momenta. And we can represent this delta function as an integral d4x of e to the ix dot the sum of the p's, which gives this delta function. So to get the delta functions, we assign an x variable to every vertex. And when we have an incoming momentum, we think of that as a function of x, namely e to the ip dot x, and then we integrate over the x's. So to do this systematically, we assign a spatial coordinate to each vertex, and we write the propagator in position space. Well, this is the propagator in position space. The propagator in momentum space is 1 over p squared plus m squared. So in position space, the propagator is this. But we don't want to forget our Schwinger parameter, so we really write the propagator this way. Except, this x should be x minus y here, as it was there. So that's the position space propagator. And we want to write all our propagators in position space, and then we integrate over the positions at the vertices. So we have a slightly new way to interpret a Feynman diagram. We integrate over a position parameter for each vertex and a length parameter for each line, and each line also has a factor, which is the position space propagator. But in addition to inventing Feynman diagrams, Feynman also taught us how to interpret this position space propagator. In fact, I think what I'm telling you is probably close to the way Feynman originally thought about Feynman diagrams. We think about a non-relativistic point particle whose Hamiltonian is p squared plus a constant, or I'll call the constant m squared. So p is what you think it is, minus I d by dx. So if this is the Hamiltonian, then this was the action. And that action is just the action the first action you met when you met actions the first time. It's the action for a non-relativistic point particle, except that usually there's m over 2 multiplying the kinetic energy. And here m over 2 is 1, so 2m is 1. Sorry. I wrote that 2m is 1, but it should be that m over 2 is 1. And also, we added a constant to the Lagrangian density that wasn't important when you were an undergraduate because the elapsed time was fixed. But here, the elapsed time is part of what we're integrating over. So the constant m squared will eventually multiply the Schwinger parameter. So Feynman taught us, that we should think of this propagator as the amplitude for a particle with this Hamiltonian to propagate from y to x in a proper time t. I should perhaps say that another difference between what we're doing now and what you were doing when you were an undergraduate is that when you were an undergraduate, the x's were spatial coordinates and t was the ordinary time. Now we're doing relativistic physics, so the x's are all 4 coordinates, space and time, and t is what would often be called the proper time. So then Feynman would say that this propagator, before integrating over t, what's really the propagator usually called is integrated over t. But the function that you integrate over t to get the propagator is the amplitude for a free particle with this Hamiltonian p squared plus m squared to get from y to x in a proper time t, where y and x are points in space-time, not in space. And now this is Feynman's basic insight. G of x, y, and t can be obtained as an integral over all paths by which the particle could have gotten from y to x in time t. A classical particle would get there in a straight line, obeying the equations of motion, but a quantum particle can get there on any path at all, weighted by the exponential of minus the action. We're Euclidean today, so there isn't an I in the formula, right? So in Lorentz signature, the minus sign is replaced by an I. But both our space-time and our Schwinger parameters are Euclidean today, so Feynman's formula then looks like this. So the amplitude to get from y to x in a Euclidean time t is given by the Feynman integral over all paths from 0 to t. The dominant contribution is given by the minimum of the action, which is the classical path, the classical solution, but quantum mechanically all paths contribute. This is the basic Feynman path integral of non-relativistic quantum mechanics, which you can read about in, for example, Feynman's book with Hibbs, although there they would primarily have real time, so the minus sign would mostly be an I. So now let's put the pieces together. When we evaluate a Feynman diagram, what do we do? Well, we integrate over all possible Riemannian metrics on the graph, which amounts to integrating over the Schwinger parameters. We integrate over all possible locations of the vertices in spacetime, and also over all possible maps of the lines connecting the vertices into spacetime. But if we put the two halves of this sentence together, the sentence just says we integrate over all maps of the graph into spacetime. So I explained it first why we integrate over the vertices where the vertices go in space-time, and then why we integrate over the rest. I said that we integrated over the vertices, the images in space-time of the vertices, because we need to impose momentum conservation at each vertex. And then we integrated over the paths between the vertices, because that's what Feynman taught us to do, to calculate basically the integrand of the propagator. But if you put those two steps together, you're simply integrating over all maps of the graph into space-time. So I guess this is what I just said. To evaluate the amplitude associated to a graph gamma, we integrate over all metrics on gamma up to diffeomorphisms of gamma. So the only invariants are the Schwinger parameters, and all possible maps of gamma into space-time. This amounts to a version of one-dimensional general relativity. The fields are a metric on gamma and a map of gamma into space-time. That map is described by fields X defined on gamma. Sorry. So here's the action. So you see, there are fields capital X, xi. The index I runs over the coordinates of Minkowski spacetime. So in 4 dimensions, it runs over x, y, z, and t. And gij is the metric of spacetime. I've actually called the proper time, well, I've called the integration variable s rather than t, because otherwise I was at risk of calling too many things t. So I parameterize, well, the action is really a sum of integrals over the different pieces, but I just write that as an integral over the whole graph. Each piece of the graph is parameterized by coordinate s. It has a 1-by-1 metric tensor h. And this is the general relativistic action for a theory of one-dimensional general relativity with a metric tensor h, fields x. And if you're confused about what the H inverse is doing here, in general relativity textbooks, that should be HSS with the indices up. But for a 1-by-1 matrix, raising the indices is the same as taking the inverse of the 1-by-1 metric tensor. So anyway, this is the action for scalar fields X in one-dimensional general relativity. Actually, any question before I go on? We have to slow this down somehow, because I'm about to run out of talk before I run out of time. Okay, no questions? Okay, I'll have to find another way to slow down. Maybe I'll use the blackboard more than I intended. So one thing is that in general relativity, there's an Einstein-Hilbert action, square root of h times r, but there's no curvature tensor in one dimension, so that's absent. By the way, this term is what in general relativity would be called a cosmological constant. It's a constant that multiplies the volume element of space-time. So here we had a cosmological constant, and we have an action for the scalar fields X, but we don't have an Einstein-Hilbert action. Second point, I keep telling you, we can go to a gauge in which h is 1, and then the integral over metrics reduces to an integral over the Schwinger parameters. Third, in introducing this, we took the space-time metric to be the flat metric, but we don't have to assume this. So gij could be constant. Then we would be describing Feynman diagrams in Minkowski space. But if you want to do Feynman diagrams in curved space-time, the same formalism works, with gij being non-constant functions of x. So then we would have general relativity with an action for non-free fields x, and it would describe Feynman diagrams in curved spacetime. So this one-dimensional general relativity on a particular graph is a way to calculate the Feynman amplitude associated to that graph. Of course, in quantum field theory, you have to sum over all possible graphs. One particular graph isn't the whole story. Now, when we do this in practice, of course, we have to integrate over the Schwinger parameters. And an important point is that the integral over each Schwinger parameter has two ends. There's t goes to infinity and also t goes to 0. T goes to infinity generates the pole of the propagator. So I've integrated over t, e to the minus t times p squared plus m squared. If we go from 0 to infinity, it would be exactly 1 over p squared plus m squared. But if we go from anything to infinity, we still get the same pole. The squiggly line just means that that this is a good approximation near the pole at p squared equals minus m squared. We don't want to do without the region of large T because the pole of the propagator is completely essential to the physical interpretation of quantum field theory. So the reason we are describing particles is that our amplitudes have singularities that come ultimately from the poles of propagators. And if you like, the physics in quantum field theory is because the amplitudes have those singularities. For example, at the most basic level, if you look at tree level, at e plus e minus going to e plus e minus, there's a W boson resonance. And so there's a pole in the amplitude at tree level that comes from the pole of the W boson propagator. So we don't want to do without the poles of propagators, so we need the large T part of the integral. The other end of the integral is responsible for the fact that the propagator is singular at short distances. So now I'm writing it in real space rather than position space, so I'm doing the p integral. And in d dimensions, well, this formula would be exact up to a constant if I integrate it from 0 to infinity, but if I integrate from 0 up to anything, I still get the singular part at short distances. So the short distance singularity of the propagator comes completely from small t, while the momentum space pole of the propagator comes completely from large T. That's where ultraviolet divergences come from. When all the proper time parameters in a loop go to 0, and all the vertices in the loop map to almost the whole same point in space-time, we potentially run into an ultraviolet divergence. For example, this diagram might diverge depending on the dimension of space-time and what's at the vertices. If x, y, and z are almost the same in space-time, and also if the Schwinger parameters for this particular loop are all very close to 0. So ultraviolet divergences come from the corner of the integration over the Schwinger parameters when the whole loop is collapsing to a point, which is mapped to almost a point in space-time. So we could get rid of ultraviolet divergences if the Schwinger parameters were bounded away from 0. And that wouldn't ruin the poles and the propagators. But in quantum field theory, we can't get rid of the small t region, because if we put a lower cutoff on t, we would spoil space-time locality, which is also an important part of the physical interpretation. If you didn't care about space-time locality, you could get rid of ultraviolet divergences in any number of ways. But with space-time locality as one of the constraints, we need the small t region. And then that gives us ultraviolet divergences. So that's why quantum field theories are at risk of ultraviolet divergences. Another important point is that we've ignored a lot of extra trappings that come with Feynman diagrams. So for example, different particles can have different masses and spins. When we have a vertex, we really should label it not just by the momenta, but by which kind of particle there is on each line. For example, maybe it's 2 electrons and a photon, or 2 neutrinos and a graviton, or something. So the vertex should be labeled by the types of particles, not just the momenta. A vertex has a coupling constant, and that coupling constant can depend on which particles are chosen. And more generally, the Feynman rules tell us to place at a vertex not just a coupling constant, but a more general factor that, in general, depends on momenta and possibly on polarizations. So there are a lot of bells and whistles in Feynman diagrams, and those bells and whistles are what model building in quantum field theory is all about. From the point of view of perturbation theory, one theory differs from another by all those bells and whistles. But we've just ignored them. What we've done is to describe the properties that are common to all quantum field theories. all quantum field theories can be interpreted in perturbation theory in terms of one-dimensional general relativity. Okay, you have another chance to slow this down a little bit with questions. Going once, going twice? Yes? Okay, the question was why we have to integrate from t up to infinity why locality makes us do that. Okay. Well, a flippant answer is that having a minimum proper time would be a lot like having a minimum distance in space-time, so you shouldn't expect the theory to be local if there's a minimum proper time you're allowed to talk about. That's a little bit flippant. Now, in more technical detail, if you looked at textbooks, you would find how the short distance singularities are associated to locality. And as I showed you, the region of small proper time is the region that leads to the short distance singularities. For today, I might try to get by with those two answers. Any other questions?
Well, to be fair, you say that all quantum theories are going to a one-dimensional GR, but then your example was with a particle just flowing trajectories, right? But now we have fields that have infinite degrees of freedom, right?
Well, they're usually not infinite degrees of freedom. They're finitely many types, typically, right? So I presented it as if the only variable describing a particle was its position. But in the real world, there are finitely many particles for a given position. There are different fields. So in our one-dimensional general relativity, it's like having spin. In the Schrodinger equation, it's spinless. It's a one-component wave function. But then you become more sophisticated in their spin, so you have a two-component wave function. So I treated it as if what was propagating on a given line was just the fields x that describe the motion in space. But what you're saying correctly is that there are finitely many types of particles that can propagate. So we have to incorporate something analogous to spin. And m squared, therefore, is not a constant, but is a matrix that we could diagonalize that has different values for the different particle types. Any other questions? Well, I guess we have to move on to string theory then. And probably it will surprise no one to be told that instead of one-dimensional general relativity, we're now going to do two-dimensional general relativity. So in the starting point, we replace graphs by two-dimensional manifolds, which are also called Riemann surfaces. Riemann surface is just a fancy name for a two-dimensional surface. So here I've drawn an example of a two-dimensional surface. This one is said to have genus 2 in the fancy language. It just means that it's got two handles, 1, 2. And one thing you immediately notice about it, I'll call it the string world sheet, I think. One thing you immediately notice is that there's no need to assume singularities. So when we did one-dimensional general relativity, to get anything interesting, we had to allow our one manifolds to have singularities, and that led to all the bells and whistles of quantum field theory, and also the ultraviolet divergences eventually. But our two manifold, there's no reason to assume it has singularities. We can try to develop a simpler theory in which our two manifold is smooth. Well, if the two manifold is smooth, then unlike a Feynman graph, which is divided into different lines, there's just one smooth surface. It has no beginning and no end. It just goes around. So the different lines in a Feynman graph can represent particles of different types with different masses and spins. But any part of a string world sheet is equivalent to any other. If you go back to this picture and look under a magnifying glass at any one piece, it's just a smooth manifold that actually, if you look at it up close, will look flat. So up close, it will just look like you're looking at a piece of the plane. So there's no beginning and no end. And there's only one string. So in a Feynman graph, there are different lines, and that's why you can have different kinds of particles of different types with different masses and spins. But here, there's only one string that was propagating around the world sheet, no matter where you look. So whatever particles there are going to be are going to represent different states of vibration of one basic string. Also, there aren't any vertices in the string world sheet, so we don't have the freedom to tell the string how to interact. In other words, when we made a quantum field theory, it was up to us to decide what was going to happen at an interaction vertex. So we say which particles meet there, what the amplitude is, and in general, we introduce factors that depend on momenta and polarizations. But then when we go to string theory, we can't do that. Any piece just looks like a piece of the plane. Locally, nothing's happening. So you can't introduce any factors that tell the string how to interact. The string is just going to do what it wants, which is often, historically, not what the people studying string theory wanted it to do. So we don't have the freedom to tell the string what its interactions should be. Now, to get an interesting analog of the one-dimensional story, which I remind you is conventional physics, that is, ordinary quantum field theory, requires one more key idea. Unlike a one-manifold, a two-manifold can be curved. And the space of metrics modulo coordinate transformations is now infinite dimensional. Here's a 2x2 metric tensor. It's symmetric, but it still has three independent components, h11, h22, and h12. But a diffeomorphism generator locally, infinitesimally, means that you shift the coordinates by two functions of the coordinates. So a diffeomorphism generator depends on two functions, which is not enough to gauge fix the three components of the metric. One field is left over. Now, there are two directions you can go in. We could accept this fact, and then we'll have to do a path integral over this field and try to make sense of it. It's a hard road to go, but it turns out you can do it. But if you go down that road, it turns out you get somewhere that you can get much faster in a much simpler way. It turns out it's much quicker and I think more incisive to follow a different route, which turns out to arrive at the same destination. The quicker route is as follows. We impose an extra symmetry that eliminates one component of the metric. So we do that by requiring conformal or violent invariance. We say that the metric h is considered equivalent to h times any positive function, which I'll write as e to the 2 sigma, where sigma is any real function. So if h is subject to that kind of equivalence, then only two of the three functions in h are independent. For example, we could use this equivalence to impose a constraint on h that its determinant is 1, leaving only two independent functions. And the two independent functions are what can be eliminated by a diffeomorphism. So we then are back in the same situation as in one dimension with only finitely many parameters after gauge fixing. So a 19th century result, in fact, says that up to diffeomorphisms and conformal transformations of the metric, a two-manifold only depends on finitely many parameters. And these finitely many parameters are cousins of the Schwinger parameters. In a sense, in the sense that in a certain limiting situation, the real parts of these parameters are like the Schwinger parameters, although their imaginary parts are something new and stringy. So I've drawn here an example of a Feynman diagram. That's a particular example of a two-loop Feynman diagram. And now I've drawn a stringy analog of this Feynman diagram. All I did was to thicken each of the lines in the diagram into hollow tubes. And where 3 lines in a Feynman graph meet at a singular vertex, I've let the tubes meet smoothly. So this string world sheet is gotten from the Feynman graph by thickening the lines into tubes and smoothing out the singularities. And in this particular region, where the world sheet looks like this, it's a sort of stringified version of this particular Feynman diagram. But that gives a good intuitive interpretation of what a string diagram looks like, but only in one limit. To make that point, I'm going to go back to a previous picture. Here, we had a string world sheet with 2 handles. And if you think carefully, see, it doesn't particularly look like that Feynman diagram with a long line and 2 ears. But if you think carefully, you'll see that topologically they're equivalent. Here, I have, again, 2 handles. But I've stretched the previous picture so that it looks more like this Feynman diagram. So a string world sheet can look like a Feynman diagram, but only when the Schwinger parameters are large. If I tried to make the Schwinger parameters small, then the tals would be too small, and we'd have a generic picture like the one I had before. Actually, I had forgotten that the blackboard wasn't conveniently available together with the slides, but I'd like to use the blackboard for a bit to draw some more pictures. So I just want to give you a little more sense of what is happening when we go from a Feynman diagram to a string diagram. I'm going to do this by drawing 2 different 2-loop Feynman diagrams. And each of those we can smooth into a string theory diagram, only the only trouble with this is that we've got to try to draw it in real time. Which, if you're not an artist, is a little bit hard, but I hope you can visualize this as a string diagram that was gotten by thickening this one. And then I'll draw once again the picture that already was on the transparency. So each of the 2 Feynman diagrams is a 2-loop diagram in a cubic field theory, so they have the same number of Schwinger parameters, but different ones. I'll put primes over on the left. But if you think carefully about the string diagrams, you'll see that the 2 string diagrams are both smooth 2-dimensional surfaces with 2 handles. Here, in this picture, you see one handle here and a second one here. And here you see the 2 handles in another way. And if you are good at some mental gymnastics, you'll see that these 2 pictures have the same topology and can be smoothly deformed one into the other. To make that more obvious, I think I'm going to draw an intermediate case, assuming I can draw it. So here I've drawn a smooth 2-manifold that is meant to be intermediate between this guy and this guy. So if I start here and shrink this vertical line, I'll get this picture. But I hope you can also see that if I start here and shrink the horizontal line, I will get this picture. Now, okay, so one fact is that all 2-loop graphs, so let's say that there's only one 2-loop string graph. So that's kind of fun. But why is it important? The reason it's important is actually that, in a sense, it's the reason that there are no ultraviolet divergences. Suppose that in field theory we try to interpolate between this guy and this guy. Well, you could say, well, let's shrink T2 prime to 0, and that gives the same thing we get if we shrink T2 to 0. And that's true as far as it goes. So here is a Feynman diagram that is symmetrically related to the two on the left and right. But to get there, we had to let one of the t's go to 0, and one of the t's was going to 0 is where we're going to get ultraviolet divergences. So if we were to try to compare different Feynman diagrams in field theory, we'd run into ultraviolet divergences. But in string theory, I showed you how to smoothly interpolate from this guy to this guy. So I told you that there was this 19th century result that up to diffeomorphisms and conformal scalings of the metric, a two-dimensional surface has only finitely many parameters. But what are the parameters? Well, in this picture here, the tals correspond to the t's. In this picture, there still are 3 parameters, but there's no real field theory interpretation of them. And then in this picture, there are 3 parameters, and they correspond. They have a field theory analog corresponding to this Feynman graph here. So, when you compare in string theory, you simply integrate over all possible shapes of a two-dimensional surface. There's no simple field theory interpretation generically, but there is a simple field theory interpretation when the two-dimensional surface turns into a thickening of one of the graphs. And when that happens is precisely the region when the t's are becoming large. Since if they aren't large, we'd get a difficult to interpret string theory picture. I think we'll go back to the slides. Unfortunately, while I was drawing those pictures on the blackboard, I saw what looked like a sea of confusion out here, whereas you seemed like a model audience as long as I was giving these slides. So I think something went wrong with that explanation. So here's our Feynman diagram with Schwinger parameters, t's. And the 19th century result says that there are finitely many parameters which, roughly speaking, when they're large, have an interpretation that matches some Feynman diagram. If they become small, they're hard to interpret, but they might expand again in a different region, and then they would match some other Feynman diagram. To be a little bit more precise, the string theory parameters are complex parameters, so they really correspond to a real parameter plus I times the Schwinger parameter. Sorry. This formula is usually written with the I over here. Well, sorry, okay. I'll take it back. I'll leave it the way I've written it. In any case, technically, the field theory parameters are complexified, but the new component is only important for the string theory details because it is bounded between 0 and 1 typically. And the physical interpretation has to do with the fact that t can go up to infinity. So maybe I should just remind you that in field theory, we understand what's going on when the Schwinger parameters are large. That's when we have particles propagating. When the Schwinger parameters are small, that's when we have technical difficulties with ultraviolet divergences. Going to string theory, when the Schwinger parameters are large, they correspond to string theory parameters, which technically are called moduli. So, okay, what did we do? We decided we were going to go from one-dimensional general relativity to two-dimensional general relativity. We replaced graphs by two-dimensional surfaces. Then we needed to impose a conformal symmetry on the metric. And then I gave you a little lesson about two-dimensional surfaces that hopefully didn't make you forget what we're trying to do. And now we're going to add matter to our two-dimensional gravity theory. Since we're trying to use conformal invariance to improve the analogy between two dimensions and one dimension by reducing the integral over two-dimensional metrics to an integral over finitely many parameters, tau I, the matter part of the action has to be conformally invariant. Now, in field theory, the matter fields we introduced were fields X that describe the motion in space-time. So we tried to do the same in two dimensions, and something nice happens. It works without any trouble. The usual action for massless scalar fields in two dimensions is conformally invariant. So G, I think unfortunately I call it elsewhere H, but anyway, G is the metric of the two-dimensional surface. The x's describe a map. The x's are coordinates telling you the position of the two-manifold sigma in space-time, which can have d dimensions. And I've let the space-time have a metric, which I now call capital G. So this action is the two-dimensional action of the action for a free point particle that we used before. And it has the non-trivial property of being conformally invariant, precisely in two dimensions. So that's essential to make it work because we used conformal invariance to improve the analogy between two dimensions and one dimension. There is still almost no purely gravitational action because the Einstein-Hilbert action naively is a total derivative. A better statement is it's a topological invariant. But anyway, for each string worldsheet, it's just a constant, which doesn't affect the quantization very much. So the action is basically just the action describing the motion of the string in space-time. The same action we had in one dimension promoted to two dimensions in the obvious way, except in one dimension we could have a cosmological constant, and here we can't because it violates conformal invariance. The cosmological constant corresponded to an arbitrary mass for the particle. Here we can't have an analog of an arbitrary mass because it would violate conformal invariance. So just as in ordinary quantum field theory without gravity, or just as in the first part of the talk when we did Feynman diagrams in terms of one-dimensional gravity, we basically have to only consider the action for the matter fields. So what are we supposed to do to develop the theory? We're supposed to, first, for a fixed string worldsheet, do a Feynman path integral over the fields that describe the motion of the string in space-time. And then two, integrate over the moduli tau 1, tau 2, and then sum over all topological choices for sigma. These are the three steps that parallel what one does in ordinary quantum field theory, where the sum over choices of sigma parallels the sum over Feynman graphs. The integration over the moduli parallels the integration over the Schwinger parameters, and the Feynman integral over the x's parallels the Feynman integral over the x's in ordinary field theory. Any more questions? Yes? Well, I defined it. I'm not sure what you mean by explaining it. Conformal invariance is the statement that you're allowed to multiply the metric by a positive function, an arbitrary positive function. We assume that symmetry. And then that symmetry is, well, and then I said that this action was conformally invariant. Unfortunately, what was called H in the last picture is now called G. But G is a 2 by 2 metric tensor. So its determinant is quadratic because it's 2 by 2. So the square root of the determinant is linear. And G inverse has weight minus 1. So precisely in 2 dimensions, because G is 2 by 2, this expression is conformally invariant. It wouldn't be conformally invariant in any other dimension. And that's one of the facts that enables us to try to make this theory. Any other questions? Yes? My ultimate goal is to, as you'll see, is to describe a theory that that generalizes quantum field theory in an interesting way, forcing gravity upon us and eliminating ultraviolet divergences. Yes?
When you drew those two field theory diagrams and
Yes.
this
Yes.
analogous string theory diagram,
Yes.
it looks like those two field theory diagrams are kind of related to each other by in a similar way that T-channel and S-channel exchange of energy particle are related to each other. It was like an effective vertex. Is that related to the fact that those two string amplitudes can conform to each other?
Well, okay. Well, I can't think of a useful response. So, so you're right that different channels usually differ by looking at different diagrams for the same process. So you could think of this as being an example. And what I've described is a cousin of the duality with which string theory started. But I don't think there's really going to be time to explain the analogy properly today. It's a good question, though. Yes?
I noticed that with these moduli tau I, in the worldsheet you had drawn 3 tau I, but you could choose other tau I, or a different number of tau I.
Well, I didn't prove for you the 19th century theorem, but the 19th century theorem said that up to diffeomorphisms and rescaling of the metric, the surface is described by as many complex parameters as the Feynman diagram has real parameters. That's the 19th century theorem that we should, if you want to become a string theorist, you'll have to become familiar with that theorem more than I can explain it today. Today we're only explaining what you should understand if you don't want to become a string theorist. So the number of complex parameters is the same as what I said, but in general, they don't have a simple interpretation, but in a region of the parameter space that I drew, they match the Schwinger parameters of one Feynman graph. Part of the magic is that in different regions, the same parameters can match the Schwinger parameters of all possible Feynman graphs with the same number of loops. Even that's a little bit beyond what we can really explain today, although I tried to motivate it on the blackboard with that little bit that I think was maybe confusing. Now, we're going to discuss why the ultraviolet divergences go away, but I'm going to give you as an example the one-loop contribution to the vacuum energy. So a simple example of a divergent one-loop contribution comes from a scalar field of mass m. And its contribution to the path integral is 1 over the square root of a determinant. But we can write 1 over the square root of a determinant as e to the minus a half trace log. And that means that the one-loop contribution to the effective action, this is e to the minus the effective action. So the one-loop effective action I'm calling I star is this thing. It's a half trace log. And now I see I forgot to write the trace over here. But trace log can be written as an integral over a Schwinger parameter, an integral dt of 1 over t times e to the minus th. So it's the same thing we had before, except that there's a factor of 1/2, and there's also a factor of 1 over t. It's a very good lesson in your understanding of quantum field theory to know where those factors came from. Here's our graph. The factor of a half is a symmetry factor. You can flip the graph over and it looks the same. Whenever you evaluate a Feynman graph, you have to divide by the symmetry group. And here there's an obvious reflection group that gives a 1/2. It's a little bit less obvious, but this particular graph has a rotation symmetry. It's less obvious because you might not think of it, but once it's pointed out, it's obvious that there's a rotation symmetry. So you have to divide by the volume of the rotation group. And in the gauge where the metric is ds squared, but s goes from 0 to t, the volume of the rotation group is t, because a point here has a length t of places it could be rotated to. So back here, the 1 over 2t has to do with dividing by the volume of the symmetry group of the graph. The 1/2 is the reflection, and the 1 over t is the rotation symmetry of the graph. So here's our Feynman graph, and then below it I've drawn the corresponding string theory graph. So as always, we get the string theory graph by thickening a line into a tube, and if there were vertices, we would smooth them out, but in this case, there aren't any vertices. Now, going back to field theory, the integral diverges as t goes to 0. That's where the ultraviolet divergence comes from. That divergence is the usual sum of half h bar omega for all modes of the scalar, and that sum is ultraviolet divergent. Okay, now the divergence is going to go away. What we're going to see in a moment is that the string theory problem is similar, except that t, instead of going from 0 to infinity, will only go from 1 to infinity. So there won't be any ultraviolet divergence. Now, in explaining it, I'm going to take a shortcut that will enable me to not explain some 19th century math. If you want to become a string theorist, you need to learn the correct version of this argument. But I'll take a shortcut. We can build a torus by taking a rectangle, such as the illuminated part of this slide, and gluing together opposite sides. We glue the top to the bottom, we glue the left to the right, and that makes a torus. I'll draw another picture in a moment. But it didn't have to be a torus. We could have taken a parallelogram. And then, given a parallelogram, we could glue together opposite sides. And that would still give us a torus topologically. So the 19th century theorem would tell us that all metrics on the torus up to diffeomorphism and Vela transformation can be made by gluing a parallelogram. But since that would get us into details that you don't need to know if you're a quantum physicist who isn't planning to work in string theory, we're going to simplify by pretending that rectangles are enough. That shortens the explanation, but it doesn't affect the conclusion. So I've drawn a rectangle. And this rectangle has a metric because our worldsheets do have metrics. So the metric, let's say the base is of length s, and the height is of length s prime. And then we glue the bottom to the top and the two vertical sides. If we had a parallelogram, we'd have worried about an angle. But the angle wouldn't play a role, basically, because angles are bounded. I mean, that's a simplified explanation, but we could also go into 19th century math and do it correctly. But we'll get the basic idea correctly if we just use rectangles. So we can view the string as the rectangle. You see, if I glue the left and right together, I've made a closed string of length s, and it propagates. I regard the vertical direction as time. So a string here propagates through a time s prime. But I could also say, if I've glued the top and bottom together, the left edge becomes a circle, and that's a closed string, and it's propagating through a time s. So the same surface describes a string of circumference s propagating for a time s prime, or a string of circumference s prime propagating for a time s. Either picture is correct, and as always, when two pictures are correct, you should use the one that's simpler to understand. But in any case, because of conformal invariance, we're allowed to rescale the metric, and a special case of that is that we can rescale the metric by constant, meaning we can multiply s and s prime by constants. So only the ratio s over s prime, or its inverse s prime over s, is meaningful. So in field theory, we integrate over the Schwinger parameter t, but in string theory, we're about to integrate over s prime over s. The string theory formula will reduce approximately to field theory if s is much bigger than s prime, or the other way around. Because remember, we have to stretch out the diagram before string theory looks like field theory. So we can think of a string of circumference s prime propagating for a proper time s. Because of conformal invariance, we can scale s and s prime by constant. So for example, we can gauge fix to s prime equals 1. And then if s prime is 1, then s is the same as s over s prime, which we identify with the proper time of a field theory. So the integral that in field theory is an integral over the proper time t is in string theory replaced by an integral over the ratio s over s prime. The difference between field theory and string theory comes because the string theory has a symmetry that exchanges s and s prime. The symmetry is just the one where you flip the horizontal and vertical axes. It exchanges the base and the height, so it exchanges s with s prime. It exchanges s over s prime with s prime over s. And so because of this symmetry, you can assume that s is bigger than s prime. In other words, in terms of t equals s over s prime, t is no less than 1. So to summarize, in field theory, we integrate over t from 0 to infinity, and we typically find ultraviolet divergences for t going to 0. We might also find infrared divergences for t going to infinity, depending on the theory. In string theory, we integrate over t from 1 to infinity. There is no ultraviolet divergence because the integral begins at 1. Depending on the theory, there may be an infrared divergence for t going to infinity. That's why there aren't any ultraviolet divergences in string theory. The essence of what I've just told you was discovered by Joel Shapiro around 1971, though it wasn't well understood until the 80s. Yes?
If you do not have imposed conformal invariance from the start, would this result change? Or is it generic?
Well, first of all, this is generic because the theory we're discussing is characterized by conformal invariance. Conformal invariance is one of the rules in this theory. Now, if you don't impose conformal invariance, you have a much harder time. You develop what at first looks like a different theory, but after a much longer analysis, you end up discovering that it's actually the same theory viewed in a more complicated way. So the theory I'm describing is the only known theory. People tried to invent another one, but it did. For a quick summary of what happened, the other one turned out to be an interesting, different way of looking at the same theory. Interesting and different, but harder.
So the other one doesn't have UP either?
Doesn't have what?
UP.
The other theory turns out to be the same one, so it has all the properties I've told you. It's the same one looked at in a way which is interesting and useful for some properties, but not simple enough that I could hope to explain it in one lecture. So I've explained this in a slightly naive way, but the point holds true in general. Technically, I'll give you the technical statement, but to understand the technicality I'm about to state is for string theorists, not for quantum physicists who just want to know the minimum. But technically, the moduli space of Riemann surfaces has a region at infinity that matches the infrared region in field theory for all possible graphs with the appropriate number of loops. But it has no region that corresponds to the ultraviolet region in field theory. So there are no ultraviolet divergences because there's no ultraviolet region. The question, how well does the integral converge in the ultraviolet, doesn't make sense. There's no ultraviolet. And thus, string theory is free of the ultraviolet divergences of field theory. Now, there's another statement that's very important. It's much less trivial. It was essentially known in the 80s, but I wasn't satisfied with how clear some of the arguments were, so I actually spent most of the last 2 years polishing up details just to make the validity of the statement clearer. But the statement, which is true but less trivial than I've told you, is that the infrared behavior of string theory matches the infrared behavior of a field theory with appropriate light particles and interactions. Yes?
So, are the strings of the interactions or the coupling constant of the field theory very constrained if you try to get it from a string theory?
Well, I think it's a good question, but I think I'll discuss it later. But if we naively start with strings in Minkowski spacetime, we just get a definite theory. And so we're stuck with what we get. But, okay, there's what's called compactification. Okay. I want to go in a slightly different direction. If we have time, you can ask again at the end. So, the statement I've made here. Well, anyway. It's an extremely important statement, which the best I can do today to roughly explain it is that the infrared behavior comes from where the t's are large, and where the t's are large matches the region where the tails are large. So that's on one foot, that's the reason the statement is true. And if you'd like to understand it more thoroughly, you can go into a lot more detail. So by now, arguably, I've done what I said at the beginning, which was to tell you a minimum you should know about string theory as a quantum physicist, even if you don't want to do string theory. But the organizers are generous with the time. And since we did get here at 3:20, which I think means we still have 20 minutes, we're going to talk a little bit about one more thing, which is why string theory describes gravity in the target spacetime, which I'll call M. So you see, at the beginning, I described quantum field theory in a language of one-dimensional general relativity. Quantum field theory does not have to describe gravity. In a sense, it can't describe gravity. You run into intractable ultraviolet divergences. While quantum field theory has, but then we went from one-dimensional general relativity to two-dimensional general relativity. And if you want to learn a little bit more about string theory than what I've told you so far, what you should learn next is why it automatically describes gravity. Now, I actually need one more picture that I haven't made a slide for, so we'll have to go back to the blackboard for a moment. And what I'm going to do when we have the blackboard is to write down an interesting example of a conformal transformation. Okay. I wish I had a slide, though, because then I would have been able to refer back to it later. So here's a flat metric, dx squared plus dy squared. Now, conformal invariance means we're allowed to multiply by any function of x and y. And I'm going to pick a nice function. So that's a metric which is conformally equivalent to the first one. And if x and y are large, it's more or less equivalent to the first one. So at large x, we still have a plane. But what I've done by this conformal mapping is to remove a point. You see, there's a singularity at the origin. So you have to know a little bit about conformal field theory to understand why this is a legitimate operation. We've removed a point, and then we have moved that point to infinity by multiplying by a singular factor, 1 over x squared plus y squared. And if you go to, you can see with a little work that the metric looks like I've drawn here. If you want to do that, you go to polar coordinates, x plus iy equals r e to the I phi. And then you'd find what I've written is 1 plus 1 over r squared times dr squared plus r squared d theta squared, d phi squared. And if you further write r equals e to the lambda, then you'll find that the metric becomes d lambda squared plus d phi squared for lambda going to minus infinity. So I've produced a metric that's conformally equivalent to the plane minus a point, but I've replaced the plane minus a point by something that has a tube that comes in from infinity. And the tube that comes in from infinity, you can think of as a physical string state that propagated for a very long proper time. So at a point, we would have inserted an operator in quantum field theory. But if there's a long tube coming in, we would put a physical state there that then propagates. So what I've explained is something called the operator state correspondence of conformal field theory. This is also true in higher dimensions for essentially the same reason. So if you study four-dimensional quantum field theory, conformal field theory for some reason, or three-dimensional quantum field theory for critical phenomena, or whatever, you'll run into the same operator state correspondence. So now we'll go back to the slides, and we'll have to remember this trick in a little while. So I'll tell you one more. It's okay, leave it. But I want to say that there's no operator state correspondence without conformal invariance. So in one-dimensional general relativity without conformal invariance, there's no operator state correspondence. But in two-dimensional general relativity, or any dimensional general relativity with conformal invariance, there's an operator state correspondence. And the reason string theory is going to describe quantum gravity, and quantum field theory doesn't have to, is that for ordinary Feynman diagrams, we didn't have an operator-state correspondence, but in string theory we do. You'll see how it comes in a moment. I do have 20 minutes, don't I, Scott? Okay. So we want to see that string theory describes gravity in the target space. In other words, the space in which the strings are moving. It's not up to us, it happens automatically. The explanation takes a couple of steps. First, we have to decide what are the fields in the target space theory. Well, in the familiar case, the fields are represented by external lines. So a field corresponds to a possible incoming particle. For brevity, I drew my Feynman diagrams before without external lines, but when you're calculating an S-matrix element, you would have external lines. And what can be on the external line corresponds to the fields that interact in the Feynman diagram. So by analogy, the fields that correspond in a string diagram, a string analog of this diagram looks like this with an external tube. And what can interact are the string states that appear on the external tubes. In other words, the fields are the vibrational states of a string. That statement should come as no surprise, but the operator state correspondence told us that we could get a tube out of nothing by making a conformal transformation. So instead of having an external state, we could have just had an operator inserted at a point on the world sheet. You'll see in a moment why that's important. There's no analog of that in field theory. Now, when we explained our rules of string theory, there was an arbitrary metric g in spacetime. Let's change the metric a little bit, from g to g plus delta g. Well, the action changes a little bit, and since the action was proportional to g, the variation in the action is proportional to delta g. So suppose we want to do string theory with a slightly different metric. Well, that means that the action that we use in the string path integral is a little bit different. And so we have to include in the path integral a factor of delta I. Delta I is the integral of something over the string world sheet. So this is going to cause an operator to be inserted somewhere on the Riemann surface. So for the case that the change in the action comes from a change in the metric, the operator is this one, the integrand of the change of the action. But from what I've just told you, by the magic of conformal invariance, the point where we inserted the operator could be at infinity at the end of a long tube, and it could represent an incoming string state. So in other words, there's an incoming string state with the property that the interaction with the incoming string state describes the response to a change in the metric of spacetime. In other words, the metric of spacetime is one of the external fields. If we shift the expectation value of the field corresponding to this string state out here, it amounts to shifting the metric in spacetime. So the dynamics of gravity in spacetime is part of what string theory describes. The reason we couldn't have done that in field theory is that in one-dimensional general relativity, we don't have an operator-state correspondence. It would still be true that we could change the metric of spacetime, and then our formalism for Feynman diagrams and curved spacetime would change a little bit, and the action would change like so, except it would be integrated on a Feynman graph instead of a surface. Everything would have been true except for the important step, where, okay, this would be the integral of an operator over the Feynman graph, but an operator inserted at a point on a Feynman graph can't be converted into an external state because there isn't an operator-state correspondence for one-dimensional general relativity. It's a property of two-dimensional conformal field theory. The key step is that a point where an operator is inserted can be projected to infinity, to the end of a long tube where a string state propagates. That's why string theory describes gravity in spacetime. So if you go down this road, and then you have to incorporate space-time supersymmetry to avoid some infrared problems, you arrive at a systematic way to calculate quantum processes involving gravitons, free of the ultraviolet divergences that one gets if one tries to quantize Einstein's theory directly. The ultraviolet divergences are absent because two-dimensional conformal invariance completely eliminates the ultraviolet region from the Feynman diagrams. Thank you.
Constraint if it comes from string theory.
Well, it depends what you mean. The question was the low energy quantum field theory. So the low energy quantum field theory can depend on details of a microscopic construction. So first of all, if you want to become a string theorist, you have to go into this in much more detail, and you'll learn about the critical dimension, which comes out to be 10. So to make a four-dimensional model, you're compactifying from 10 to 4 dimensions. You have a lot of choices in how you do that. And the low energy quantum field theory in 4 dimensions depends on the compactification you pick from 10 to 4 dimensions.
So I know that you can take a plane and map it to a sphere conformally.
Yes.
Is that a stereographic map?
Yes?
So you have something that is infinite, and then now it has a distance. Is there a way to regulate it for divergences?
Well, the fact you've just stated is actually the same fact I used, basically. What I said was, which is that a point can be projected to the end of a long tube. If you'd used a factor that was even more singular than the one I used, instead of long tube, it would have opened out at infinity. So what you've said about the stereographic projection is a very close cousin of the fact that I used to get the operator state correspondence. I think that the version I told you is the one that's, certainly it's the one that's most important to understand if you don't want to be a string theorist. Because you'll run into it for other reasons. You might study conformal field theory in condensed matter physics, or even because you want to make some new model of the TeV scale, for all I know. And the operator state correspondence might be important there. It's a basic fact about conformal field theory. And I feel that the version, you're completely correct about the stereographic projection. Okay, that's also an important fact. It's a cousin of what I've said. I'm not completely sure it'll help most people if in principle, we could do it, but if you use a rather similar but slightly different, more singular factor than the one I used, you get the stereographic mapping from the sphere to the plane that you've mentioned. Yes?
So what is the relationship between the topology parameter of the Feynman diagram and the action of the one-dimensional general relativity?
Between the what parameter?
The topology parameter of the Feynman diagram.
I'm not sure what you mean by the topological parameter.
The Euler characteristic.
Well, the Euler characteristic of a Feynman diagram is determined by the number of loops. And of course, the number of loops is important in Feynman diagrams, as it is in string theory. That's the main topological invariant that you will meet in quantum field theory. You don't usually meet others for the following reason. In interesting quantum field theories, you usually have gauge invariants such that individual Feynman diagrams with a given number of loops aren't gauge invariant. Only the sum is. So, roughly speaking, okay, to get something reasonable, you usually have to sum over a lot of graphs. String theory does that for you by turning all the different graphs you were summing over in field theory into different limiting cases of the string world sheet. Any other questions?
The different topologies of the two surfaces are just,
Yes.
Euler things. So it's just summing how many
Yes.
loops.
I only did closed strings. And then for closed, it's a little more complicated for open strings. For closed strings, the topology, as you say, is the Euler characteristic, or equivalently the number of handles, and it corresponds to the number of loops in a Feynman graph. So graphs are much more complicated to classify, but for a lot of purposes, the number of loops is the important invariant. And when you go to string theory, you lose the more fine details, because all Feynman diagrams of a given number of loops come from one string diagram for closed strings. Yes, you had a question.
Oh, yeah, since the t less than 1 part of the field theory was correspondent to locality, does that mean that string theory is not local?
Well, string theory has the question is whether string theory is local. It's a little bit subtle what that should mean. You see, string theory is not local in the sense of having operators that commute outside the light cone, local operators that commute outside the light cone. Neither could any theory with quantum gravity be local, because x, the position, is not gauge invariant by that definition. You see, the position x is not a gauge invariant notion. So phi of x in general relativity is not a gauge invariant concept. So in any theory with gravity, locality can't be described by saying that there are operators that commute outside the light cone. This historically was not a clue to the fact that string theory described gravity, because people didn't understand it well enough at the time. But on another planet, you could imagine that having discovered that quantum gravity can't be local and that string theory couldn't be local, that might have been a clue that would help somebody put the things together. There's a different way we could try to assess locality, which is by looking at the consequences. When we do have locality in quantum field theory, we can try to use it to prove analytic properties of the S matrix, which unfortunately are not that well understood in ordinary quantum field theory. But to the extent that they're understood, I believe that they're the same, at least in perturbation theory, with or without gravity. And I believe that string theory has similar properties. I think that personally that the answer is the following. String theory, I believe, can't be interpreted properly as a theory in ordinary spacetime. It produces an S matrix that you can macroscopically interpret in ordinary spacetime. But microscopically, the rules are different, and we don't know what they are. So what I think personally is the answer is that it's physically sensible, and it will do anything that you think should follow from locality. By the way, that won't be true in field theory if you try to set t bigger than 1. You'll get bad things. But what locality really means in string theory isn't that well understood. Instead of talking about setting t bigger than 1, let me remind you of more of a textbook way to get rid of ultraviolet divergences in field theory, which is Pelley-Villares regularization. You add a regulator field with the wrong sign of the propagator and a larger mass. If you take it seriously, it's not physically sensible because the field you've added has negative probability. Making t bigger than 1 in field theory is analogous to that. String theory is not analogous to that. Everything that you can calculate is completely physically sensible.
So you showed us the string version of Feynman diagrams, but are there non-perturbative ways that you can use to define string theory?
Yes, there are lots of non-perturbative results in string theory. And arguably, some of them, like the correspondence between gauge theory and gravity, are even things that a quantum physicist who doesn't want to be a string theorist should know about. I only told you what you should know about string perturbation theory if you don't want to be a string theorist. Yes?
How do you regulate the IR divergence in string theory?
The what divergence?
The IR divergence.
Well, first of all, some infrared divergences are real in field theory. What you aim to do is to get the same similar infrared problems to those in field theory, whatever those are. So the complete answer for what the infrared behavior of field theory is a little bit complicated. And I think at least the answer standing on one foot is that the behavior for large tau in string theory is the same as the behavior for large t in field theory. And the divergences are exactly the same, and you do with them whatever you do in field theory. That's an answer while standing on one foot. I can tell you more if you ask a follow-up question, but I can't guess quite what your follow-up question would be, because there are too many conceivable directions. Yes? So the question is, can you make a theory based on membranes instead of strings? Experience is the answer is no, but you're welcome to try. But of course, your question was asked before. So in the late 80s, mid to late 80s, a lot of people asked that question and tried to invent membrane theories. They didn't invent theories where you can base the theory on membranes in the same sense that you can base string theory on strings. But they did discover something that was extremely fundamental in the context of string theory. So string theory has membranes, and membranes are important in understanding string theory at the non-perturbative level. So they would have been part of the answer to a previous question. But nobody knows how to make a theory that's based on membranes in the same sense string theory is based on strings. Numerous things go simultaneously wrong. I can't say you can't do it, but nobody can give you much advice about doing it. No, well, see, the answer is no. As I told you, string theory has membranes, but there's no evidence that there is an asymptotic expansion, a perturbative expansion based on membranes, either for string theory or any other theory. My guess would be no, but one can try. But in any case, ABJM is in the orthodox context in which string theory has membranes, but can't be based on membranes in the same sense it can be based on strings. That is, membranes are not the starting point for a systematic calculation in perturbation theory, the way fields are a basis for a systematic perturbation theory in field theory, or strings in string theory. That's the orthodox answer, and ABJM is completely within that framework. Any other questions? Well, the question is, what's the impact of the Higgs discovery? Well, let's put it a little bit more broadly. String theorists, but I think all particle physicists traditionally suspected that at the weak scale we would find a mechanism that would account for the nature of the weak scale, for the hierarchy problem. And the elusiveness of that structure, well, it's definitely a challenge to traditional ways of thinking in particle physics, which were shared by string theorists, but not only string theorists. And, I mean, we're counting on the LHC or something to discover something that will shed light on a world in which the standard model holds sway. Okay, I think maybe we can call it a day. I don't see more questions.